So now I can go through my exercise here and kind of re-emphasize what I learned, what were my takeaways, and of course also what is still fuzzy to me. As always, I will not deal with that here in the online lecture. I leave that up to you. You should do that, however. What I will do with you is reiterate what we have done. So to me now it's clear that the internal forces for rectangular hinged frames can be determined just like I did it before. And I, of course, now completely buy into the idea that the shear force in a vertical member translates into the normal force at the frame corner into the horizontal member, and so on and so forth. So I can check that off too. The bending moment, of course, the bending moment remains constant at the corner because opposite to the shear force and the normal force, the bending moment actually rotates about a point, and it doesn't matter if the point is on the vertical member or on the horizontal member, as long as they're like very much close to the corner. And if I put all of that together, I can also efficiently draw my diagrams for rectangular hinged frames. Don't be fooled. Of course, it takes practice and problem solving to really get familiar with that. But I believe we have really deciphered this, and you can now draw your diagrams. At least you know how to. Of course, practice makes perfect, and that's what the homework is for. So therefore, let's go ahead and move on, and let's take a look at the upcoming homework. To no surprise, our homework focuses on orthogonal frames. You see the first 4 out of 6 problems here on this page. So let's take a look at all of them. They all have a right-angled corner. Some of them even have 2 right-angled corners. But the first 3 problems are slightly different from the last 3, as you will see when we take a closer look. So let's take a look at the very first frame here, for which you're supposed to find the support reactions and then draw the internal force diagrams. Now, what you can see here is that it has a pin on the horizontal member and a roller under the vertical member. Now, for these frames, it is important that you identify where your reference fiber is. Of course, you have used the reference fiber before, but you didn't really need it. In this case, especially for the vertical member, you want to identify if it's on the right side or on the left side. I choose to always put it on the inside, but there's no right and wrong about this, so you could also put it on the other side. In fact, you may want to practice and see what happens if you put the reference fiber on the left side, because remember what the reference fiber does. The reference fiber is a local coordinate system. So for example, for this member, this reference fiber defines the coordinate system, and then for this member, this reference fiber defines the coordinate system. And it defines the positive x direction and the positive y direction. And so you can imagine that if I put the reference fiber on the other side, which you're very free to do for these vertical members, then the diagrams might look very different, or at least they appear to be different. Of course, physically, it doesn't change, right? Like, you cannot differentiate the system physically by drawing the fiber on the other side. Physically, everything has to be still true. So this is just a trick we use as engineers to have a better communication. But you need to communicate where the bending moment is positive and where the bending moment is negative, so that later on engineers actually know, for example, where to put the reinforcement steel and so on. You will learn this in later classes, but it is very important that you identify where the positive and where the negative direction is. So I suggest that for this frame, you just put it on the inside, and then I think everything else is as before. You don't need to solve the support reactions through 2 equations with 2 unknowns. In fact, the first one here you can find is the vertical support reaction at A. You just take the sum of the moments about this point, and then you have your vertical reaction. Then you can find the vertical reaction here, and there's in this case no horizontal reaction. And then please remember something I showed to you in this lecture, that the diagram for this vertical column is different or separate from the horizontal beam. So sometimes I see students who try to make a connection here from the diagram of the vertical member to the horizontal member, but you should really look at them separately, and I believe I have shown that to you throughout the lecture. So please pay attention to that. All right, let's go to problem number B, which is a very interesting frame, which is actually upside down, as some students sometimes call it. But in reality, it's just a horizontal member that has a vertical member welded to it. So this corner here is 100% stiff, and it needs to be connected rigidly. And the roller is just sitting underneath the horizontal beam. So think of this as a simply supported beam with a corner welded to it. And once again, you kind of want to identify where your reference fiber is. For this problem here, the way I would do it is just on the bottom, as I always do, and then I also choose the inside. You could have, for example, also moved this reference fiber to the top just for practice purposes, or you could put this to the outside, then it would pretty much line up with this one. It's up to you, but my personal convention is inside and bottom. That's how I usually do it. Notice that you have a force here, which is horizontal, that therefore causes a moment here of that corner. So you can really think of this part as a cantilever. This force also produces a horizontal reaction here. And I think if I tell you anything more, I solved the problem for you, and you clearly don't want me to do that, right? So let's take a look at the next problem. So now we have a frame with two right-angled corners or orthogonal corners. One is here on the left and one is on the right. But to find your support reactions, you really don't need to consider anything differently than you've done for beams in the past. The only thing that changes is how you find the internal forces in the vertical member. Once again, I probably would put my reference fiber on the inside so that I can unify my findings, but it is really up to you where you put it. However, the internal forces, they are slightly different than they were before in a beam, but I think the lecture provides you all the knowledge you need to solve this problem. Just understand that, again, this is an easy problem compared to the lecture that we've done, or the example problem that we've done, because it's not a hinged frame. It's just a simply supported frame, as you can see here. So I have a roller and not a pin and a pin. If I had a pin here, I needed a hinge somewhere. In fact, that is what we see in our next problem. So in problem D, we actually have a frame that has a hinge here at the corner and is loaded with an evenly distributed force from A to B and has a triangular distributed force on the vertical component. Notice that this problem is very similar but not identical to the problem that we saw in the example problem throughout this lecture, and that is these two supports are actually at the same elevation. In this case, elevation is kind of like in the x direction here, so they both have the same x value. Let's consider this here the origin of the coordinate system, so they both at x equal to 0 if we look at a global coordinate system. And so there's actually an easy way and a difficult way to find the support reaction for this one. So if you take the sum of the moments about this point, you can either take this part or you can take this part. And for one of those equations, either this one or this one, you will end up with one equation with one unknown. And for the other one, you would actually end up with two unknowns in it. And I'll let you figure out how that is and which support reaction to find first. There's an easy way and a hard way, so always work smarter, not harder. However, once you've done that, please identify where your reference fiber is. I always do it on the inside, so I suggest that you use this way. However, there's nothing wrong with doing it any other way as long as you're consistent with your answers. So please keep that in mind, that you always have to identify the reference fiber first before you can make sense of your internal force diagrams if you deal with more than just a horizontal member. Now that completes all the problems that are listed on this page, but we always have to solve 6 homework problems. So let's go to the next page to take a look at our remaining simply supported hinged orthogonal frames. So here we can see our last two problems for the current homework, and now it becomes really interesting because we now have truly hinged beams that have pin support at A and pin support at B. This symbolizes the hinge here. In this case, the system only has load on it on the left side. This is to make your life easier so that you can quickly identify your two equations with two unknowns to find your first support reaction and then move on. And then everything you learned from before in the homework applies as well. Once you found the support reactions, is really not different. So of course you need a reference fiber again, because that really determines how your diagrams are drawn in terms of positive and negative regions. So that completes this problem. Let's now move on to the last problem in the homework set, which is a very similar frame. In fact, for educational purpose, I made this very similar to the previous one, with the exception that now the system is loaded to the right of the hinge and to the left of the hinge. And this will make your equations a little bit more complicated, but this is on purpose so that you're better prepared for your exam, that you can identify how to fast set up your equations and what is the easy way and what is the difficult way. So this problem should really teach you where to start such a problem if you compare it to the problem on the other side. In fact, let's compare it to the problem on the other side. So this is done on purpose, that we have it actually mirrored, the frame itself is mirrored over this vertical plane, but it's differently loaded. And in fact, pay attention to the load of this frame here, which has a horizontal force that passes through this support, whereas here there's a force that actually is removed from this support and this support. And in addition to this one is pushing on the frame and this one is pulling away from the frame. So please pay attention to that and see what effect it has on your final diagrams. Of course, once you reach this problem here, problem F, you're so far advanced with all your internal force diagrams that I don't really need to give you any more tips here or suggestions. I don't even need to tell you where to put the reference fiber and so on and so forth. So you will be a mechanics champion at this point when you solve these problems. But that completes now our homework. And I think this prepares you well for the upcoming task. We have one more subject to cover before we go into the exam. And that is, we will actually take it from orthogonal frames to non-orthogonal frames, or in other words, roof structures. So in our next lecture, we will not have a right angle in the frame. We will actually have sloped members. So not a horizontal adjacent to a vertical, we will have a horizontal adjacent to a slope member, or just a slope member to a slope member, for example. And you will see that in a roof structure, but more details on that in our next lecture. Just come prepared, please. So this is really targeted to prepare you for that, so that we can really focus on the last issue that we need to cover during our next lecture. I hope that you will have fun studying this material, and I wish you good luck with that. I see you in the next lecture. Until then, stay safe.